4:1. Okay, we're going to begin the idea of forces. That's the whole concept of this chapter. Sections 4:1, 4:2, and 4:3 are pretty easy sections, to be honest. 4:4 is when we start to really do a lot more math. So you know how we had 3:3? It was a ton of math and what we've been doing lately, and I didn't really do 3:1 and 3:2. We're going to do 4:1, 4:2, and 4:3, but they're minimal. There's not too much that's difficult there. When we get to 4:4, we're going to look at a lot of stuff where there's a lot more math involved. Okay, so in order to understand what we're going to do later on with the math, you need to know the theory. Bless you. 4:1 and 4:2 are primarily theory. Okay, 4:3 begins the math, 4:4 is a lot more. So 4:1 is called changes in motion. We're going to discover how forces actually affect motion. And we're going to differentiate between what's called a contact and a field force. And then finally, we're going to interpret and discuss what are called free body diagrams. Okay, those are the three goals. First, a force is simply the cause of an acceleration. Okay, a force is the cause of an acceleration. And generally, this is described as a push or a pull. A push or a pull. Okay? You can have a force with no acceleration. Like watch, I could push against the board. It's not moving anywhere, right? That's because there's supports in the board that apply an equal and opposite force back. I'm still applying a force. If I apply a force to an object that is not fixed in space, though, like this water bottle, it moves. Okay? Whether it's moving at a constant velocity or not, it has to accelerate just to even start moving. So it's currently at rest. I push it lightly, it starts to move. Just starting to move is accelerating. So anytime you apply a force to an object that's not fixed in space, it's going to move. It's going to start moving, even if it's the smallest motion ever. Okay? You could have, this chair right here that's on wheels, so this is probably pretty easy to move, but I could apply a tiny force with my finger, just a little force, it's going to move, okay, because it's not fixed in space. Now, on Earth, obviously, and anywhere where there's an atmosphere, we know that there's friction. So friction could also cause an object not to move. Like this desk here, if I tried to move it, probably wouldn't move much because there's a lot of friction between the locks and the actual wheels on those little, whatever those things are, the locking mechanisms on the wheel itself. The unit of measurement for force is the Newton, okay? After, obviously, Isaac Newton. Okay, it's measured after, or it's named after him. And the unit for Newton is really kilogram meter per second squared. Okay, again, the unit of a Newton is really a kilogram meter per second squared. Now, I want to discuss something. In units, when you see that minus sign, it looks like a minus sign, kg minus m it looks like. It's not a minus sign. I just wanted you to see this because you're going to see it in other books and if you take physics in college. It's actually a multiplication symbol but with units. I know. Trust me, it's weird. So instead of writing this, because look, this wouldn't work too well. People wouldn't know necessarily what is going on. And instead of putting a time symbol, whenever there's a combination of units, they put a dash in between them. Okay, a dash. But this is really what it means. Okay, that's really what it means, so you know. So a Newton is really a mass times a length over a time period squared. Again, to highlight this, a mass in kilograms, a length in meters over a time squared measured in seconds squared. So a Newton is really a unit that's comprised of other units. That's why in the beginning of the year we discussed some of our basic fundamental units. We talked about mass being kilogram, length being meter, and time being measured in seconds. And what we're going to notice throughout the rest of the year is that as we look at more and more units like joules, or watts, or others, many types of units, those units are made up of many units themselves. So it's a combination, whether it's a product or a quotient of different units that actually represent the other. So like a watt is a joule per second, but a joule itself is a kilogram times meter squared per second squared. So they're made up or comprised of smaller units that turn out to be that overall unit. So this is the first example of that. Okay, so when we get to Newton's laws, when we look at force equals mass times acceleration this year, we'll see that this is where that unit ends up coming from. Okay, that's where the unit ends up coming from. Something to note, something maybe to jot down. These are like the conceptual kind of questions I ask on tests. Since a force is the cause of an acceleration, you could also say that since acceleration is a change in velocity, a force causes a change in velocity. Again, forces cause acceleration, but acceleration is really a change in velocity. So you could say that forces cause changes in velocity. Again, I push on this water bottle, its velocity currently is 0. The minute it starts moving, and now it's got a velocity. So if you change the velocity of something, you're applying a force somehow. When you hit the brakes on your car, where's the force coming from there? Anybody know?
It's just, it's like negative deceleration.
Yeah, but where's the force coming from? Yeah, it is negative acceleration, absolutely. But physically, where's the force coming from? When you apply the brakes, what's happening?
Looks like the things are closing on the wheel.
Yeah, what are those things called?
Brakes.
Brake pads. Brakes, good. So the brake pads engage with the wheel. Listen, the brake pads engage with the side of the wheel with the rim, and they cause friction, and it slows the wheel down. That's how you slow down physically. Okay, now, if your brake pads are worn down after 2 or 3 years, you'll notice that your brakes become spongy. You hit the brakes, you don't feel them right away. You have to really apply the force. Because you apply a little force, and the brake pads go to engage, but because they kind of wore off, they're not engaged with it. You have to apply more brake on your actual brakes so that they push harder. So if you ever feel that your brakes aren't working on your car well, it's usually because your brake pads wear down. Ever look at the rims of a car? Sometimes the rims of a car will have like dust on them. It looks black. That's the brake pad. It deteriorates over time. The brake pad, as it's applied there, it starts to wear off. And you see parts of it, little particles like dust, they cover the rim of a tire. So I used to drive a Jeep when I lived in D.C. I sold it when I came back to New York, or gave it to my brother actually. And when I drove it, I noticed that my front wheels on the Jeep were always like black. And there was a problem with the model of the Jeep that I actually had, that the brake pads were always over-engaging. And by over-engaging, they were applying too much of a force, and it would start to wear down more. So I had to constantly clean the rims of the car, or the front wheels. Just a little example of that. But again, a force causes acceleration or causes a change in velocity. Okay, a change in velocity. Now there's two types about a contact and a field force. Okay, a contact force is literally something that exists as contact between two surfaces. Take your hands, go like this. You're creating friction, right? That's what you're doing. It's two objects in contact. There's a force between them. You feel it heating up. That's a contact force. Very easy example. A baseball player hitting a ball. You're applying a force and you're redirecting the motion of the ball. Its velocity was certainly this way, and now it's certainly this way. So you're changing the velocity. Thus, you're applying a force. What's a field force? And you can read the definition, but what are some examples of field forces?
Like static, like when you rub your feet on carpet.
And then what happens when you go near something?
When you get like a shock.
Get a little charge because you're charged up. So a static electric charge is a good example. What else?
Magnetic fields.
Magnetic fields. You bring a magnet near something. You bring the magnet near this board, what's going to happen? It's going to pull you toward the board. You're not in contact, but you feel a force. And then suddenly, you're in contact because it's stuck. But you could be at a distance away from a certain value or a certain surface and still feel a force pulling on you. What's another force that's a field force that's always existing around you? Gravity. Gravity is a field force as well. Okay? Again, I'm not touching something that's causing me to pull to the earth. I'm touching the earth, but that's nothing to do with it. Even if I was in the air, if I was literally standing and I jumped off the desk, right? Gravity would pull me down. I'm not in contact with the ground while I'm being pulled down, but gravity is still affecting me. So that's a field force. Field forces act at a distance. So you're going to see later in the year when we get to gravity and the electric force and force of magnetism, that they all involve a distance away from that object. Usually the closer you are, the stronger the force. They're usually inversely related. And you can feel that with a magnet. You bring a magnet close to a surface, you can feel it get stronger as you get close to that surface. And eventually pulls you to the surface. Okay, so those are the two types of forces that we're going to be looking at. Free body diagrams, okay, and talk about what they are. A free body is a body, God bless you, that's not connected or attached to other surfaces. So if I wanted to draw a free body diagram of Summer's purse, clutch, what is this called? Bag, of Summer's object right here, okay, it's currently sitting on the table. Gravity's pulling it down, and the table is pushing back up. So if I were to draw a free body diagram of this object, you would have gravity, and I'll talk about how we label these in a minute, gravity pulling down, and we'd have the table pushing back up. We call that a normal force. But I'll explain these forces. Don't worry about the labels. Okay, but for now I want you to understand the idea that if an object is at rest, when we draw a free body diagram, we're literally just drawing this object. We're not drawing the table below it. We're not drawing anything attached to it. If I was pulling on this handle, what is it called?
I don't know.
What is this called on a girl's purse? Handle?
Yeah,
Handle. If I was pulling on this handle at an angle like this, there would be a force being pulled outward like this. Imagine that I was pulling on the handle of it. Okay? That's what it would look like. But you don't physically see my hand there. Okay? When you draw a free body diagram, you are literally drawing the forces acting on that single object. Okay? On that single object that affect its motion.
Is this box the thing?
The box is the object, yeah. With
This is small.
Wait, what?
So this is the center of it. Okay, gravity always acts in the center of mass. So we draw it there. This is a right angle, showing that what's called the normal force. Again, don't worry about it for now. But the normal force is something that pushes back up. All right, and FP is like a force of pull, a pull on it. I don't need to label these. Don't worry about the labels. If this is confusing you, don't even write them, because we're not even going over these today. Okay, so you could just draw those. That's fine. Yeah, G was gravity. Yeah. Okay, so gravity's pulling down, the table's pushing back up, and I'm pulling on that handle at an angle, whatever that angle might be. And usually, if you have an angle that's known, you draw it in. Okay, if you know it's at angle theta, whatever it may be. Okay, but that's what a free body diagram generally is. All right, now let's take a look at. So, in figure A, we have a force diagram, not a free body diagram, but a force diagram. And that shows all the forces in the whole situation. So what's happening here? Let's talk about this. The car is driving. You know how they do the test on the cars? Where they drive cars into the wall just to see how they respond? So this is one of those scenarios. The car is driving forward, and then it hits the wall. So the car feels a push on it backward when it hits the wall. The wall feels a push on it that way. That's this right here. The car feels it being pushed back. The wall feels it being pushed that way. Now, if the wall was not strong enough, the car would break through the wall, obviously. But the wall still does push back. Even if it's not strong enough, it's still going to push back. And you've seen that in car accidents. Even if a car goes through a stop sign, you're still going to see the mark left behind from the stop sign. Okay, so the force acting on the car is right here. When the car is force acting on the wall is right here. The force up is the ground pushing back up. The force down is gravity pulling back down. Now, figure B is a free body diagram. Figure A was a force diagram. It's all the forces in figure A. Figure B is like this. All right, you know what? We want to analyze the car and look at its motion, not the wall. So we simply draw the car. Okay, we draw the car and all the forces acting on it. And what we notice is that there's an unbalance of force. Up and down are balanced, right? The ground is pushing up, gravity is pushing down. They're balanced. They're in equilibrium, we'll talk about. But we see this push on the car to the left. That means that when this car runs into the wall, it's going to hit the wall, and it's going to probably rebound off the wall. Okay, that's this unbalanced force showing that there's going to be some negative acceleration that way. Okay, it might just be stopping the car, it might stop the car might actually bounce off the wall. Depends on the actual scenario to see which of those it is. Okay, but a free body diagram, again, is specifically looking at the forces on one object, and usually it's the object that's in motion, or the object of interest. Okay, so, again, if I were pulling on this garbage can, it's attached to the floor, and when I pull on it, it's feeling friction from the floor, and the floor is feeling the reaction. But I wouldn't draw the floor, because I'm really concerned about this object right here. So I draw this object, I might draw friction acting backward, my arm pulling this way, gravity pulling down, and the floor pushing back up. So we'd have four forces on this object. But we don't care about the surrounding scenario. So what we're really doing is we're isolating some little part of our system. Okay, and if you study engineering, you learn that this is extremely important. If you isolate a certain part, because you look at things like, you could take this topic and apply it to fluids. Fluid flowing into a chamber and fluid flowing out of a chamber. So if you have some sort of a throttle and fluid is flowing in, causing the fluid to become turbulent with the throttle, and then it comes out, you can see the mass coming in and the mass going out if you analyze that little area. So you're going to take this idea of specifically honing in on one object of interest, okay, if you end up studying engineering or some science field, you probably see this, and you could expand that to volumetric flow rates, or mass flow rates, or like rocket ships, when they exhaust their rocket fuel. You look at that as an individual system. It starts with a certain amount of mass, but when it burns up that fuel, the mass decreases inside of it, so the rocket ship actually gets lighter as it flies through the air, because it's losing mass, it's losing all that fuel as it pumps it out. Okay? But again, the idea stems back from our free body diagrams of isolating one object, okay, the object of interest. All right, that's it. Do